Today we're going to talk about an application of derivatives to a special function that's important in special relativity. So this function is called the gamma function, and it's defined as gamma of v is equal to 1 divided by the square root of 1 minus v squared over c squared. So here v represents the speed or the velocity of a moving body, and then c represents the speed of light. So this function gamma of v comes into play in a variety of different contexts. In particular, it comes into play when you're studying time dilation and length contraction. So as an object increases in speed, it exhibits two separate phenomena. First of all, time appears to slow down, and secondly, length in the actual vessel that's traveling at a high speed contracts, so it appears shorter than it actually is to outside observers who don't have that same speed as the vehicle. Now, this basically is the work of Einstein in his 1905 special theory of relativity, which was a result of an experiment called the Michelin-Morley experiment. So Michelin and Morley in the 1800s tried to figure out what the Earth's absolute velocity was. So they were operating under the assumption that there's some absolute velocity to everything in motion. So it's kind of like there's an absolute resting frame, that everything else is moving relative to this resting frame. So they tried to, so let's say we have the sun, and then here's the Earth. So we know that the Earth is moving around the sun, and it has a velocity like this, and it's traveling in a circular path. So they set up an experiment to measure the time it took photons to travel back and forth between a sequence of mirrors. And then they waited a half of a year so that when the Earth was on the other side of the sun going in the opposite direction, they repeated the experiment, hoping to basically be able to figure out what the absolute speed of the Earth was, by looking at the difference in the time it took the photons to go back and forth between the mirrors. Because if I'm going this way, if I'm moving forward at a certain speed, and I'm measuring how long it takes something to move back and forth, I should get a different result than if I'm moving backward. But they observed that the photons always traveled at the same speed, regardless of whether the Earth was going this way or that way. And so basically the result is that the speed of light appears the same in every reference frame. Now this is very different than what you expect in classical mechanics. For example, if you have a train that's going 55 meters per second, and then you have a jogger who's running forward at 2 meters per second, and then you have somebody outside of the train just sitting watching the train go by, this observer outside is going to view the jogger traveling at 57 meters per second. He sees the 55 meters per second of the train plus the 2 meters per second of the jogger relative to the train. So the observer outside will clock that jogger going at 57 meters per second relative to the ground. Now the situation is very different when you're in a speeding spaceship. So if you're in a spaceship that's traveling at 0.9 times the speed of light, and then it shoots out a photon torpedo that's traveling at 0.9 times the speed of light relative to the spaceship, what would an observer clock the torpedo? So what speed would an observer on the ground see the torpedo going? So basically the spaceship is traveling at 9/10 of the speed of light relative to the ground observer. The torpedo is traveling at 9/10 the speed of light relative to the spaceship. So you would think that the observer would clock the torpedo at 1.8 times the speed of light. However, that is not true. The torpedo still appears to be going slower than the speed of light. So basically, no matter what reference frame or how you view light, it's always going at the speed of light. So even if you're going at 9/10 of the speed of light, to phrase this slightly differently, and you turned on your headlights, you would view the headlights as moving forward from you at the speed of light. The observer would also view those headlights traveling at the speed of light. So velocity does not add linearly when you get to high velocities. And there's a bunch of consequences of this, namely special relativity, and this function shows up when studying this sort of scenario in detail. So that's just a brief introduction as to where something like this comes from. I won't derive it, but when you study physics, you'll encounter this in special relativity. Now, first thing we should note is that this function has a vertical asymptote. So in other words, the limit as v approaches the speed of light from the left. So in other words, if you have a velocity less than the speed of light and you're gradually creeping up to the speed of light, of gamma of v is equal to infinity. Right? So in other words, so this is 1, this is the speed of light, this function has a vertical asymptote at the speed of light. And you can see this because when the velocity is equal to the speed of light, we get c squared over c squared, which is just equal to 1. So we get 1 minus 1 is 0. 1 over 0 is undefined. So if the velocity is very, very, very close to the speed of light, v over c squared will be very, very, very close to 1. So you get a number that's very close to 0. 1 divided by something incredibly small will be an incredibly large number. So the closer you get to the speed of light, the larger this ratio gets. So this comes into play in particular when you look at the relativistic energy of a speeding body. So the relativistic energy is mc squared times gamma of v, where m is called the resting mass. So it's the mass of the object when the object is at rest. And this is, of course, the energy as observed by a stationary observer. And so basically, if you start at any resting point, any reference frame, the amount of energy required to reach the speed of light is infinite because of this factor, you have this asymptote in the energy, and so therefore you basically exhibit diminishing returns. So the faster you go, the more energy is required to achieve a smaller and smaller change in your velocity relative to your starting frame. And to get to the actual speed of light would require an infinite amount of energy for an object with mass to reach the speed of light. Photons, on the other hand, are massless particles that travel the speed of light, so it's a little bit different. So it shows up there. It also shows up in time dilation. So if you measure 2 clicks of a clock on a spaceship, and then you have an outside observer, would see those clicks take place in a very slow fashion. So everything on the spaceship slows down as viewed by an outside observer. So this factor shows up there. So without further ado, let's actually take a look at this. So suppose we want to take the derivative of this function gamma of v with respect to v. And we're going to use the power down rule because gamma of v, we can rewrite this as 1 minus v squared over c squared raised to the minus 1/2. Right? So we have some quantity raised to the minus 1/2. So it's the negative sign in the exponent comes because this guy is in the denominator. So the negative sign takes the reciprocal, and the 1/2 is the square root. So the negative 1/2 together is 1 over the square root. Now, when you get good and you've practiced this a lot, you wouldn't actually have to write this. You can just look at this and say, okay, that's something, this stuff to the minus 1/2, and do a lot of this in your head. So the stuff in red I would actually normally do in my head, just mentally. So gamma prime of v, well, the minus 1/2 comes down, minus 1/2. Everything inside the parentheses just stays the same. And then I subtract 1 from the exponent. So minus 1/2 minus 1 becomes minus 3/2. And we're not done because remember the power down rule says we power down, so that's what I just did. I took the minus 1/2, moved it up front, subtracted 1. Now I have to multiply by the derivative of the inside function. So the inside function is this function right here. So the derivative of 1 is 0 because 1 is just a constant. And we're taking the derivative with respect to v because we're differentiating this function with respect to v. C is a constant. So the derivative of the inside, we get v squared is going to be 2v, and then everything else is just a constant. It's a multiple. So it's minus 1 over c squared times v squared. Derivative of v squared is 2v. So the derivative of the inside, we get minus, instead of writing the minus here, I'm going to put that out and cancel out the minus up front. So minus 2v over c squared. And the reason I do that is because when you put the parentheses and the minus inside, it's very confusing to, it's very easy to make that, to think that, oh, it's this minus that. So it's good practice, good style to always take the minus signs and move them to the front of any given term. So instead of saying times parenthesis -1, just move the -1 out front. So you kind of have to keep track of the minuses mentally, put them in the front of each term instead of, so instead of writing x times -3, write negative x times 3, or even better, negative 3x in that case, because numbers usually go in front of variables. But do try to put the minus signs, collect them together. 2 minus signs make a positive. So we got 1 minus sign from the minus coming down here, and then another one from the derivative of the inside. So the derivative of the inside, the derivative of 1 minus v squared over c squared, is just 2v over c squared. The exponent came down for the -1/2, and then we had a minus that came out there. So, and then putting this together, the 2's cancel. So we have v over c squared. The minus here puts it to the denominator. The 3/2, the 1/2 you can do the square root, and then the 3 could be cubed. Or you can just write 1 minus v squared over c squared to the 3/2 like that. So that is gamma prime of v. Now the units of this, gamma itself is a dimensionless number. So gamma is going to be a dimensionless factor. And we can test that because v over c, v and c have the same units because they're both velocities. So v over c is dimensionless. 1 minus a number is a number. Everything here doesn't have any units on it. So v, or gamma, doesn't have units, but it's d gamma dv. So remember, the derivative represents d gamma dv. So it's the units of gamma, which there aren't any, divided by the units of v. So it's divided by meters per second. So when you're dividing by meters per second, it's the same as multiplying by seconds per meter. So velocity is measured in meters per second. This quantity will have units of seconds per meter. And this basically tells you, the rate at which this gamma factor is increasing per increase in velocity at a given velocity. So if you're traveling at a certain speed and you want to figure out, well, how much will the energy increase if I increase by a little bit of velocity, this will give you that rate when you multiply it by mc squared. So that is the gamma function. And it's just, so there's a little bit of a story behind it, but really it's just taking the derivative of this quantity right here. And we use the power down rule, which, to go back, if we have f of x is equal to u of x to the n, so in this case n was -1/2, the n comes down, so we get f prime of x n u of x to the n minus 1, and then times the derivative of the inside. Then for the derivative of the inside, we again use the derivative of polynomials. So 1 minus v squared over c squared, I see 1 is a constant, so the derivative is 0, minus 1 over c squared is a constant, so I just take that constant coefficient and multiply it by the derivative of v squared, so times 2v. So the derivative of the inside function was just minus 2v over c squared, which shows up here, except the minus sign went out front. So that is the derivative of the gamma function.